So let's start with another example here. And this is going to be a little challenging. But let's start over with this. There's a couple pieces we're going to need to include. Nope. That is not what I grabbed. So even when copy and paste doesn't work, we are having a very Monday in engineering. Pretty soon, it's going to be time to go find some chocolate pudding at Walmart and call it a day. All right. There. Copy and paste can still work, even though it's a Monday in engineering. Okay. We're going to use the microphone. It is physically connected to pin 4. However, we can't just do an analog input, for instance, on the microphone, because that's not how it works. We've talked about that a little bit, looking at some of the documentation that you guys have seen for the Circuit Playground Express. So we're gonna keep things moving and rolling here, but we are going to be using pin 4 for the microphone. Okay. In order to do that, we have to use a new function. We're going to add one more variable, and we're going to say this is called sound. So I'm going to rescale this a little bit, make it a little easier for us to see more of the things. Here we go. So we're going to define sound. So first, what is this program doing? So we're going to give ourselves some comments so that we have some context, because this is part of good programming discipline. Bring in the CPX libraries to allow using the mic function. This is define the pin used for mic input signal. And then we're going to again do something with that sensor data, and we're going to monitor using the serial monitor what's coming in, so that we have some reference points. Okay. In the setup, what we're trying to do is we're going to start with serial. There's a couple other pieces that we're going to need as well. So we're going to need our standard serial.begin. Start serial port to allow reading of input. Additional to this, we are going to do our Circuit Playground begin, And then we have another one that we need as part of this. So this this starts the CPX library so we can use its functions. Without doing that, you can't really access the functions. This sets our mic pin to input so we can read sound data. Okay. So we have a couple pieces that we need to run once in our setup, right? So we're starting the serial so we can actually get input in. This is something we always have to do. This is the equivalent to establishing the running game in football. One day, maybe somebody can explain to me, if they're expecting you to establish the running game, why you still have to establish the running game. And if the answer is actually as simple as, well, because you have to establish the running game, I'm just going to keep shaking my head because it's just doesn't make sense. In code, there are some things we have to do because they are axiomatic to actually doing I/O programming. Pin mode we need to use in order to make sure we know we're using this pin as input so that the pin is not assigned to some other gibberish in memory or assigned to output or doing something strange. We want to define what it's doing so that it doesn't get to pick for itself because reasons. So, okay. There's that. There's a couple other pieces to this puzzle that we're going to need. We're going to use, I guess let's go ahead and see what the analog read will bring in first. Yeah, let's do that first as a test, just so that we can see what it is. So we are going to, that is not, nope, that is not what I asked for. That is not at all what I asked for. Let's try that again. Copy paste. It's really not a super difficult operation, but some days you'd be surprised. So we're going to try it this way first. So there is a plan in case you guys think that I sit here and create new ideas on the spot for what to do. We're going to read through from the analog pin. That's going to give us a starting point. And what we're going to do is then do a serial print line, which is one we are familiar with. So, no, not caps lock. Caps lock bad. Use capitals. Makes it look cleaner. Prints out the incoming serial data with a carriage return. So what this will do is this will give us one of the next pieces we need. So now we've got one more piece. So this, let's see, let's get a vote in chat for what the last remaining piece is here. What do you guys think? It's the last piece of the puzzle here before we do a quick test.
Do we need to add a delay?
Exactly. Because 9600, that particular bit rate is crazy fast compared to how fast you can read, because you really can't read hundreds and hundreds of data points a second. It's just not reasonable. So delay, and we need, we're going to do a delay of about 400 milliseconds. And then always forget our line ending character for the carriage return. All right, so this will get us a starting point. We're going to come back to the built-in function. Let's start by taking a look at what the microphone input looks like. Make sure you've got the right COM port selected. We're going to verify, even though there shouldn't necessarily be issues with this. It is yet another Monday in engineering, so we're going to check. Okay, it compiled. So now watch it let the smoke out of the Arduino as it loads. Okay. Done uploading. All right, so we're now going to take a look at the serial monitor, and we're going to check, does it actually pick up louder volumes? Yes or no. Hello, hello. See, even if you shout right into the microphone, whole lot of not much happens, because that's sort of not how this one works exactly. So that's part of why we need to be able to use some of the built-in functions. So there's something that comes in from the serial port. However, 350 to 450 is not helpful, right? So there's a there should be a sound pressure reading that we're effectively getting there, and we're just not. So yeah, even with the microphone right there. So here's what we're going to do instead. There is another function that we can use. And before we start getting super duper fancy, I'm going to pull another example. There is a function. I wonder if I can pull it from a sketch. Here we go.
Sorry, what do I need to do if I'm getting the error code that says that it's like, it says I don't have a file or directory for the include?
So for that, you need to download the library that I attached to a zip file. I think that was in an announcement, files you'll need for week 1 or something like that. You're going to need to unzip that and then copy and paste it into the libraries folder, or you're going to need to point to it using the feature. You're going to need to point to it using the feature edit, and no, it's under tools. No, sketch and include library, and then add zip library. Any of those methods will get the same net effect, but that's what it's looking for, is this circuit playground .h, because I would explain this, why we have to have the two and why there's one with an underscore and why there's one without. But it's a thing that wouldn't make sense even if I did explain it in a way that made sense. So rather than trying to teach you guys Martian by correspondence today, just trust me, you want to include these and you want to pay careful attention to the spelling of each of them. There was a thing, somebody was being helpful and it caused a problem all over the internet, and I fixed it because yeah, it works. Don't ask questions you don't want the answer to.
Where do I find that the zip again?
That zip is in the announcements, and it's something like the files you'll need for week 1 or something like that. So there's a library in there that's already a zipped file. I don't remember if I had to do 2 layers of zipping to that one or not. It's been too many days and I've at least slept once or twice since then. Although a good programmer never sleeps, they just have more Diet Pepsi and Skittles, so I'm told. So I must not be a very good programmer. All right, so serial monitor, not that helpful for this. Let me pull another example. The reason I have to take a look at this is okay. There's okay. I can do this one without doing bins and frames, but it's going to be a little confusing. We will do another version of this. Let me see. Can I do? There's a I think the fast Fourier transform version is a separate function. So recall that I've told you when we have questions, sometimes we need to actually just go in and read the actual raw files. This is going to be one of those times. I will share this in a second. I should probably at least show some of the navigation here. All right. So in your Arduino file, I'm going to try and keep the Martian to a minimum because teaching basic programming is a lot more difficult than it seems like it should be. So in your Arduino file, usually documents Arduino libraries. This is that location I was referencing where you're going to drop that library. It needs to show up just like this. Then you'll need to close and reopen the Arduino IDE in order for it to reinitialize the library because reasons. Has to do with INI file configuration and stuff that will make sense later. So yeah, you can search in the IDE. That's also an option. That was not an option until I want to say like version 2.2 or something, but that also points to the why you need to include both the versions, the one with the underscore and the one without, because reasons. So we're going to open the CPP file, because this is what's actually going to give you the information that you're actually seeking. So now I'm going to share that so you have an idea what I'm talking about. If I shared the entire screen, probably the whole universe would explode. This is going to look like a bunch of code, sort of, but not exactly. We're going to look at how to build libraries and things later with custom functions. We're not going to do that right now because you don't really want to do that. So there's a couple layers and levels of functions. And what I'm looking for specifically is I'm looking for a specific command. So let's see if I can find you one that looks familiar. So we've used this one once. cplay red LED output. Okay. cplay buzzer. This is one that I will teach you soon. This is the greatest way to, we're actually going to use the buzzer and show you how to compose the only song you need to know using the buzzer. So that's also a factor. We didn't use the shared capacitive sense function yet, but that is a function. Slide switch pin with an input, and there's yet another concept for these called pull up and pull down. This is something that we didn't quite get into in the early versions of ESG 162 lab. Is anyone familiar with pull up versus pull down resistors? You can type no in chat if that sounds like Martian. I don't expect you guys to have been exposed to this yet, but this is part of where, because coding and because circuit and because already defined stuff and things, yeah. There's some things that we have to do. You'll see in here a couple array-based commands for things like the neopixels, which are here. So strip, update type, update length, and set pin. The cplay neopixel pin should look familiar, because that's effectively, instead of going through and teaching you arraying and things that were not quite there yet, I went straight to the root command that actually tells the neopixel what to do and how. And we'll show you the difference between the CPP and the H files are which one defines the way in which these are used, and the other one defines what the function actually does. So this is the CPP is helpful, but it's not the whole entire process. So we'll look at the .h as well. So the difference between something like a pull up and a pull down resistor to close this now open loophole because curious minds want to know. Pull down resistor means it's a resistor meant to pull the voltage on that part of a circuit down to 0 or ground. Pull up resistor means it's trying to pull it up to whatever the nominal voltage is. 5 volts, 12 volts. A lot of stuff on these Arduinos, depending on where it is on the board, is 3.3 volts. Give or take. A lot of the lithium battery packs are like 3.27 volts, give or take. That's kind of their designed output range. So when we plug in a battery pack, they're usually somewhere in that range of 3 to 3.5 volts ish. Same thing with a AA or AAA battery pack. It's trying to get to that 3 to 3.5 volts range. The pull up resistor is trying to reach that higher level. The pull down resistor is trying to pull it down to a ground state. The reason why this matters is, think of an instance where you've touched a circuit and you've had some kind of a static discharge and it suddenly changed the channel on the TV or did something weird, right? Some of us have experienced something like that. A lot of modern circuitry is a little better because of having these pull up and pull down resistors in the design process, but much older electronics generally didn't have this, or something would skip to another track, or there's all kinds of weirdness that can happen, especially with static discharge. The state of an input button or something can actually be above 0 volts, and that can be enough to cause effectively a false trigger press or something, right? There's probably been some times in your gaming where if you've had like a worn controller or something, you've had some false button presses happen, or maybe that's where you've seen it as a controller shock. I think after like PS2 era gaming, that got to be better. But the very, very first versions of some of the wireless controllers would sometimes do weird stuff if you managed to get a static discharge into them. So anyway, the pull up and pull down resistors are trying to do those things. So you have the options sometimes to set an input as a pull up or a pull down. The buttons are naturally trying to set to a pull down so that the value is sort of forced to be 0 so that you don't get false button inputs that trigger your code to actually run. That's the simplest way I can think of to do that. There's a couple IR related things. So IR receiver, IR decode. This is the dangerous one. This allows you to be able to spoof other IR remotes by getting command codes out of them. So figuring out the remote codes to your roommate's TV or something, especially like should you need to be able to assist him with, the volume or something, or figure out what the code is for mute. That would be a horrible, terrible thing to do to a roommate, but it's a thing. That would be using the IR decode function. So this is the one that we're interested in, is mic equals, so it gives you an example definition. Mic equals Adafruit CPlay mic. What this will do is this is actually the one that we're interested in. Let's see. And I don't think you can use just CPlay mic. I'm going to check the .h file real quick. Yeah. This is doing something called creating a microphone creating a microphone object. So there's a whole lot of things that have to happen in the background. I'm going to see. Okay. So it's only got a couple examples of where this is included. They don't talk about it a lot. There's a couple other things that we can do later that are going to be a little bit more fancy, trying to split out the RGB components of the light sensor. We're probably not going to get to that today, but we are going to get to a couple examples. So let me show you the .h file here, because this is all the windows, all them windows. Okay. So the .h file, this is similar to, this is basically the definitional file. There's a couple other things that are operating in the background, but the NeoPixel, again, instead of running that sort of top level thing, what we can do is we can search in here. So this will find the examples wherever NeoPix is used. NeoPix pin 8. So then down here, the NeoPixel strip. This one allows you to address using arrays what the NeoPixels are. Then down here, there's a couple commands that are given. One is clear pixels. So this is a single instance where we could do that, and we could use, so you can see each of these is a function definition by itself. So it's a void. So it's creating a class. It's an empty class, so it's not looking for any feedback. Set Excel tap is an example here. Clear pixels is one. So we could use clear pixels and then void. So whatever's coming through here, it's not looking for an input or an output. So we would just say clear pixels. And because of that, we would say open close parentheses. What it would do is it would use the strip command, which up here is defined in another other thing. And so all of these functions are functions that call other functions to do all these things, and then show and the empty array to show so that all the pixels clear. So I could have introduced this function additionally to what we did, but then there's a couple other things that we have to do with the strip and definition and arrays and things in order to make use of those very effectively. So instead, I taught you guys how to use one command, and it was this one, the set pixel color. So this is the actual core of all of the other fancy things. This is the core command that's doing it. So it's looking for an unsigned 8-bit integer and an unsigned 32-bit integer, and then it uses the strip command and strip show. So set pixel color and then show. So this one, the way that we set up the code originally was not very elegant. It's very brute force, but it's simple enough for you guys to understand what it is that we're doing. And then it gives some information. So this is a comment block that gives some information on what this function is actually doing. So this one briefly sets the pixels. Pixel 0 and all of the things are then set to a low value with that command. With this one, what it's doing is using a parameter from 0 to 255 for the red, then green, then blue. So the reason I know which one's which, when we go to set pixel color, instead of the way this is set up here, there's a couple options. So you can set it with 2. There's another definition here. Very hard to do, very not advisable to give it an example of multiple inputs, but it's defined two different use cases. Very inadvisable to do that with the same exact naming, because for you guys to do it, it's a bad idea. So what it'll do is use the strip command, set pixel color, and then do this. So for each instance, we were assigning a pin number, which is this unsigned 8-bit, and then the RGB values in all of these 3 unsigned 8-bit integers. And that sets the red, green, and blue components. And so if you were to actually watch this on a camera where you had an adjustable frame rate, you would be able to see what the blinking rate actually was of those LEDs. So these are the ways that we come in and actually understand what's going on and what the functions are doing is from the H file. So we're going to go down to the mic examples. And this one should have the mic, and some libraries include like a cplay listen command, and there's a couple others, but there should be one for the mic. There should be a definition. No, that's for accelerometer. Okay, so this is, yeah, this is setting up what's called a Boolean. So this is a value type that we haven't talked about yet. Boolean just means true or false, 1 or 0. A binary logical choice is what this is referring to, Boolean data type. So this, yeah, okay. So that gives us, let me see if I've got any additional information in the underscore. No, it does not. Okay. They do have in this some examples as well for you guys to pull from in the library. So let me show you what that looks like so that you at least have seen it and know where to look. Yeah. So under the circuit playground in the libraries examples, they give you a good example, or a good library gives you examples for how to work with those. There's a few. The microphones is probably the most relevant. So sound pressure level is a good example. The mic FFT is one of the ones that I was using. Fast Fourier transform, that requires some additional stuff that we haven't learned yet. So I'm going to open this one and show you guys one of their built-in examples here for the library. So these can be very, very helpful as a reference point. So this is what they look like. So include this is yeah, there's a lot of explanation as to what this is doing. It's a concept of trying to use the microphone to play birthday candle levels. You'll note some of these notes that are defined. So those of you that are musically oriented maybe recognize what some of these are. Some of those notes are sharps. Some of them are just notes. They really don't include oftentimes flat notes because reasons. This goes in and puts together an array. This was probably imported from, actually this one was probably hand typed, come to think of it. Then it does some global parameter stuff, but what we're looking for specifically is how it uses the circuit playground commands. So play tone is one that it uses. It doesn't have to define a pin or something like that, but there's a variable for frequency, there's a variable for duration, and then beats, and then a Boolean value false because part of how it works. So weight breath, do they define it in here? Let's see. No, I think they don't define it in here, but they do include a delay of duration plus those are 16ths. So in order to get timing to be musical, you have to do everything in multiples of 4 because reasons. Band nerds will know why. So this, yeah, weight breath is defined. So they have another void. I know, super confusing. They're defining a function within this, and so this is a level of coding that we haven't gotten to yet. But they're using in here, I believe, no, the measure peak is using, yeah. So mic sound pressure level. This is the one that's defined that doesn't require the fast Fourier transform, and this is actually the command that we'll be using. So this needs to be floating point is okay for this. The difference between a float and an int is a floating point variable allows you to store decimals. So we'll go ahead and use that, but we're going to redefine this so that it's used a little bit differently. And so what they're doing is assigning it to a variable, printing that variable, and then they're using a max value using a mathematical function called max in order to figure out what it is, and then doing animate pixels, which is another other function that they've defined. So lots of voids going on in this example. This is part of the reason why I don't have you guys just digging through these for assignments and things yet, is when we're talking about 500 or so line program, that's not actually as scary as it seems. However, you notice that there is, after all, a loop way down here. So this is actually the thing that it's doing, is it's playing the birthday cake song, and then or what they call the birthday cake song, and then waiting for a second for you to blow out the candles and the lights do things. And so it's a fun little gimmick, but it's 500 lines of code to make that all work. If they had not done all of these extra voids for these, so they're set up at the very end, and their loop. So the setup and loop are still there. But all of these other voids are defining functions so that they can use them because they need them to do stuff. Otherwise, they would have to copy and paste all of these for loops like we've been doing, and you would end up with a few thousand lines of code for the number of times they have to run these, especially for these loops of loops with conditions and things. But that function, the sound pressure level, this is what we're going to take out of this example as a reference point so that you can see how it works. So present the other thing. Back to the sketch that we started like 6 years ago. All right. Little did you know, programming was going to be so exciting. So instead of this way, where we've defined a microphone pin, we're going to not do that. What we are going to do, and we're going to not define a pin mode for input for this one. What we are going to do is replace this with this. So we're going to redefine sound up here as a float. This is not a wrong way to do it, but this is defining a variable in the defining a new variable in the loop. It's doable once you've gotten more experience in code. That's an acceptable thing to do. But this is a case of do as I say, not as I do. For now, later you can do lots of variable definitions in here. It's much better practice to formalize it and start it up here so that you guys don't forget the steps until you've done a lot of coding. Sometimes it's very difficult not to write code across like 6 different things that you're doing all at the same time, and this is why commenting is so important. So this is why we're trying to teach you guys good programming habits. So sound pressure level, and what it's looking for is it's looking for here it's looking for a value that's in milliseconds. So measure the sound pressure level for 10 milliseconds to get a sampling. It might be better in our case to bump this up to something like 30 milliseconds. That's a little bit more reasonable if we're trying to capture parts of speech and things. Somewhere around 0.3 milliseconds is going to give us a little broader average. Again, really trying not to get into frames and moving averages and sensor averaging and all the things yet, because I don't actually want you guys to just be smoking holes in chairs that used to be students. There's always another level of cool stuff you can do later. So delay 400 milliseconds. Serial print sound. Okay, so we've got what we need in order to listen to the mic, and what it's now going to output is a sound pressure level as approximated by the those microphone functions. So it should be calibrated to within a reasonable variance of how this will work. All right. Here we go. Let's do this and make it happen. Verify first as a matter of good practice. And then we will go, yeah, ignore the thing where it says it's out of memory using 14 and 16%. Verify successful CPU reset. It's totally fine. So it's saying the threshold right now is 70 dB. Yeah. If I add volume, suddenly, if I add volume at a very high rate of loudness, I could be like a jet taking off. That's 120 decibels. Almost got there. Almost got there. 120 dB is roughly sitting at the end of a runway where a jet is taking off. While I'm a loud jerk, that's a bit much. 100 dB, not quite, not exactly. So their internal calibration is off by a bit. You should actually see a noise floor in an average room somewhere on the order of 45 to 52 dB, not 70. If you've got a lot of fans and stuff running, all right, you might be, 55, 58, 60 maybe. Unlikely to be higher than that. So even if this is covered, yeah, you're not seeing anything. Yeah, the static value shouldn't be like 70 decibels. So little out of calibration. I would say scale that back by about 2/3, but it would be interesting to see what their max threshold actually is. And if we won't really usually be able to see that from the serial monitor, we're actually going to have to go to the serial plotter, which of course is a different entity altogether. So if you get really loud, then it goes up, 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 up. And you guys aren't seeing serial plotter yet because Windows are awesome. There we go. So you can see based on the input level where the sound is, when it's far away and nobody can hear anything. And then when you're really right up on top of it and it's really, really loud, almost like a jet taking off, not really. That should probably only be about 70 to 80 dB, maybe at that peak. So this would need rescaled. The way that you would effectively correct that is you would take a data set. So I'm going to do that as a matter of fact and show you guys how would you rescale this, because this falls under the category of your data is always lying. It's just a matter of how much is it lying. So we're going to switch back over to the serial monitor. And I'm going to give it a few seconds of just kind of nominal room noise. Unfortunately, I'm going to see if I can copy that into Excel. Okay, so sometimes you have to stop the Circuit Playground Express by unplugging it or something to get the data stream to stop. You can highlight data and move it around. Let's go here. So we've got our data. All right, here we go again. More stupid Excel tricks. This gives us at least some range to work with. So what we need is we need an average value. And I'll make this a little bigger so you guys can see. So average value, especially those of you that are working on small screens. So average, this is another formula, is going to be equal to, no, we just need the average for this one. I'm going to select those cells above. There's a couple other hotkeys you can use. I'm not going to worry about trying to teach you guys hotkeys and all the fancy things right now. So we just don't really have the scope and scale available for it. Okay. There we go. So number of decimals, I want to reduce that slightly so that we're still using the same kind of number of decimals. This should actually be, as a matter of fact, I'm going to see. Apps may not necessarily be any better calibrated. I don't think I have a sound pressure meter at the moment. I'm not going to download the one. Some of you could actually look at it, especially if you have like guitar tuning apps and stuff like that. But the average noise floor in here is going to be higher than it is in a lot of other rooms. So the actual is 52. So correction factor, this is also something that we would call effectively a fudge factor. If we need the output to be the actual value range, we need to rescale. That needs to be what's on top. And we need to divide by the nominal input range at the bottom. And that's the correct way to set up the ratio. What this means is it's overreading by something on the order of about 20%, but because sound pressure levels are in fact not, they're non-linear, they are exponential in their behavior, that 20% off is a lot. So batch to batch, variation to variation, that particular factor is significantly off for what I'm seeing here. So we're going to go in and apply our correction factor, our newly found correction factor, to the code. Okay. Back to sharing the code. See if I could do cool stuff and do the hotkeys and record this all asynchronously like this probably should be. This would be a whole lot less painful for you guys. Your eyes wouldn't end up bleeding at the end of the 2.5 hours so much. All right. So the good news is we're almost started. Okay. Here, when we store the sound, what we found is empirical findings suggest correction factor of this is needed. So we're going to take that correction factor and we are going to then multiply, for the sake of cleanliness, sound equals sound times correction factor carriage return. So now we rescale, then we print out, now we upload this because we remembered our carriage return. Still going to complain about memory. Nobody knows why. 16% of capacity is not a 5-alarm emergency. So we now have data in the 40s to 50s, which is where we should see it more reasonably. If we cover it, sort of isolates a little bit. Then when you're talking, a loud talking voice, you can see we're no longer anywhere near that 110. And if I'm really up right on top of it, I might be able to peak something like 90, but it's much, much harder to do. And I need to maintain a very high volume in order to get it up into 70 or 80, which is actually about a more normal conversational level is somewhere around 63 to 70 dB if memory serves correctly. So band nerds can correct me in the comments where I'm wrong, but I'm not wrong by much. So that has rescaled it, and now you can see we're not getting anywhere near those 100 levels, because even though we applied a 20%, even less than 20%, it was actually only a what? 17.75, roughly 17.74% correction factor. That was able to bring it back into a range where, even though our actual measurements based on those functions weren't quite correct, we can kind of bring it back into a range, because we shouldn't see jet taking off level noise of 120 decibels in normal conversation. It's utterly unreasonable. So the fact that I can't get it much above 85 to 90 is actually about correct. So that's more accurate, and shows you an example of a linear correction factor to a non-linear measurement. And that starts to get into why things like the fast Fourier transform version is important. That one is, I think, significantly more accurate. We can play around with that, but then you start to see that we have a lot of different numbers and things like that. So the next thing that we're going to have to get into is starting to understand some operations with arrays. And I think, as far as topic matter, some of that is coming up. So let me see. Let me see what. Let me see what Halo says. Yeah, compiler errors to diagnose syntax bugs. Okay, so there's a couple useful assignments there. Serial monitor, find bugs. Okay, so we're kind of way out accelerating what the originally intended pace of the course is. That's actually fine. We're trying to show some examples of how to use much, much more advanced details, because you're not going to be creating libraries until somewhere around week 8 is really when that kind of starts. So yeah, we're also already starting to use physical data and trying to start learning how to do correction and calibration. So it's not that I'm pushing you guys way too hard, way too early. It's that I have very high expectations, and I'm trying to show you guys using some slightly more simple tools before we start learning arraying and averaging and all sorts of things like that. You can now kind of see the need for that, because 1 minute it's 48, the next minute it's 57, and those two values are going to have a significant change on the output. So now let's incorporate some of what we did now that we've seen that the monitor is actually working. The output we need to do some things with, because sensor input is helpful. It's helpful to know, but until we do something with output, we can't really do a whole lot with that sensor data, right? So this is where we're going to copy over from our, we're going to copy over one of our examples from the temperature work that we were doing. And I'm going to go ahead and save this. I want you guys to be in the habit of saving early, save often. But I'm going to save this as I'm going to do it as CPX Mike Neopix. DB lowercase d, capital case B, because reasons. There we go. So CPX Mike Neopix DB level. This name tells me that it's Circuit Playground Express. We're using the mic, we're using the NeoPixels. So mic is input, NeoPixels is output. We're using the DB level as our variables. So short, simple, tons of information packed into the name instead of class, day, in prison 37 or whatever, right? So we're going to take the for loop that I copied. We're going to change sensor value. What we can do is we can change all occurrences because that makes things easy. They have made this obscenely simple for you guys. The level to which this is cheating is completely absurd. So that was a right-click function, change all occurrences. This is helpful when you're copying and pasting stuff exactly like this, because then you can go in, use all of your variables, change your index variables all at the same time, etc. Those sorts of features weren't built into the development environments. I'm not even sure they were developed in the development environments prior to COVID. So a whole lot of people were very, very, very bored during that time. But there have been some community benefits to that serial boredom. So for this, I'm going to run from 0 to, I'm going to do 0 to 3 for the first one. If the sound is less than, let's see. Yeah, we're going to do it a little bit differently here. I'm going to do the same sort of structure. This was our lazy version because I don't think I saved it with the updated version, so I'm going to have to recreate that. I guess that's fine. So this is our lazy version. If the sound is less than, so we actually have to take this outside of the structure, outside the for loop, and put the for loop into this kind of structure because reasons. If sound pressure level is less than, we're going to say less than, no. If sound pressure level is less than 50, it's only going to light up the first 4 in green. So we're going to move this to we want to loop this. There we go. Okay, So if sound is less than 50, sets all pixels green. If sound is less than 50 dB. This one needs to be 0. This one needs to be, we'll do 200 for green. All right. For this 0 to 3, okay. If, now we're going to end that if. We're going to do else if, because else if sound is greater than or equal to is less than if sound is less than 70. So if it's less than 50, it will do what's in here. If not, it'll skip over to our else if, which will do sound less than 70. So if it's at 80 or above, it'll skip to the else case. The reason I want to use the else case is reasonably straightforward. I'm going to tab this in one more. I'm going to tab this in one more. This one, we're going to do similar for loop to this, but we're going to go from 0 to 3, and we're going to do another one in here from 4 to 6. This is going to be, this one's going to be yellow. I forget what that nominal code was. There is an RGB value. I want to say it was like 200, 160. Something like that, like 200, 160, 0, 255, 217, 0. There we go. That'll do. Which one am I in? Downside to having 8 million of these open. So the 4 to 6 is 255, 217, 0. So I wasn't too far off. I would have gotten a yellow-orange color. Pale yellow, probably pale yellow. That's what I would have gotten there. So set 4 to 6 to be yellow, and then else. So this I can actually detab by 1, space it, else, and then we're going to do the same thing, only we're going to add another element here. We're going to add one more. And we're going to do from 7 to 9. It's going to be full red. 7 to 9. And in that, we're going to need one more operation. So we want to check before we do anything else that all of our curly brace sandwiches have all the lettuce, cheese, pickles, onions, tomatoes, special sauce, and whatever else is on there. I don't remember exactly. Last time I worked at McDonald's was never, so it's understandable. All right, so let's see. We've got 0 to 3 indexed with an increment. This is 4 to 6 indexed with an increment at yellow. So green, yellow. We're going to do 255 on this one. Just because. There we go. All right, so our else is closed. Our which one's that one go to? To the loop. Okay, that's bad. So this is one of the instances of mismatch that we don't want because that's bad. This else is closed. This needs to go away because. So this one, I'm going to drop the tab one level. Okay. So it matches and I know that it's closed. That way it's easy to see at a glance. Open for the else, open, close for the next thing. Okay. So tabbing and structure becomes very, very important as you start getting more into the like hundreds of lines for programs. All right. This is going to get us the last piece. Then we're going to do another delay. $400. And then we're going to clear pixels. So going back to our language reference, or our hardware reference, nope, that's in the .h, isn't it? No, I'm in the .h. I need the search. No. There we go. So one more thing we're going to need is clear pixels. And then what this means is we can run this to clear the pixels now that we've seen that, now that we have an idea what that's doing, instead of running these for loops additionally. So this isn't really a lot more lines of code either than, at least for the test that we're doing here. This is really not a lot more lines of code than you would need for doing string and array commands to address the string in 3 different arrays. You're still going to have to do some definition lines. You're still going to have to do the command lines. So you're really not saving a lot by doing that compared to using this. Really, this would be a better instance to use probably a case structure, but that's stuff we'll learn about later. So we're not going to worry about that right now. All right, so we're going to check the compiler. I expect it to come up with probably 1 error. Yep, okay, good. So clear pixels. This is where if it can't find the function clear pixels, we can do it. It should be included with the underscore playground.h. So it should be included here. But Since it's having trouble doing that, what I'm going to do is I'm going to copy what that function is. We're going to do this before the void setup, just like what you saw in the examples. So I'm going to cheat because I don't, because rules were meant to be broken sometimes. That's why. So we're going to add another void in here. Don't panic. Don't have a heart attack. This is going to clear up that particular compiler error because it doesn't understand what clear pixels is. Strip clear, strip show, it should understand what that is. So we're going to recompile. Now I think that will go away unless it decides strip.clear. Ha 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 ha. Libraries are the best. Okay. So we're going to go back to the for loop because grandma always said, the hurrier I go, the behinder I get. It's a phrase I wish I could unhear. Now you wish you could unhear it, but it is what it is. The hurrier I go, the behinder I get. There it is again. So instead of clear pixels, we're going to do it with a few lines using a simple for loop, 1 to 9 or 0 to 9 in order to do n 0, 0, 0. Set them all to zeros because reasons. This is why I say things like don't ask questions you don't want the answer to. Because the harder you pull on the thread, pretty soon nobody's wearing a sweater anymore and it's really a mess. Now we verify again, this should compile fine because I haven't done anything illegal as far as procedures. It will say, oh my gosh, you're out of memory, 14%. Yeah, go take a flying leap. All right, compile and load anyway. It's fine. Why the dynamic memory storage? Because reasons. Libraries are awesome. Good. Verified with flash checksum. Okay, good. So it will blink. I also tried to pick a frequency that would not induce seizures and fun, exciting things. So what we've got is a level where if we talk really loud, we should be able to get it to light up red, but it won't stay on very long. So I'm going to change the timing on this just slightly. Nope, not on that one. No, I really don't want to do the fast Fourier transform one, blah, 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 blah. Okay. So our delay of 400 on the uptake is fine. We're going to leave them on for 800 milliseconds. So I'm just going to make a slight adjustment to the timing. I'm also going to adjust the thresholds just slightly, actually, because reasons. So if sound pressure is less than 60, if this is less than 80, that way you guys can see 75, because reasons. Okay, done uploading. So what this will do is give us green. Then when I talk a little bit louder, we get yellow. It'll stay on yellow long enough for you to see. And then if we're really loud and very angry, we'll get red. So we might need a little bit longer even still. So the timing control is iffy on these. So I'm going to do a delay of 800 and 1200. There we go. You could much more easily do this while you were watching some kind of show or something and playing around with the volume and using that as a reference point. But I wanted to be able to show how it would blink with a different color and be able to stay long enough for it to be able to see what's going on. So you might have to play around a little bit with thresholds to see what makes the most sense, but you could do this with finer gradation. That would start to be more code than individually addressing those as strings, but the library functions don't always work correctly, as we just demonstrated there. So, all right, that's by some other professors, that probably is almost the equivalent of 2 weeks of lessons. So we're going to pause here for a minute. For what we did today, what do you guys feel like you're at on the clarity scale from 1 to 10? I see a few of you have already turned into marshmallows and fallen into the campfire, so that's understandable. But where do we feel like we're sitting on a clarity scale of 1 to 10? This is also a good time for questions, so go ahead and ask those.
I just wanted to ask a quick question about what the code is actually doing. So you set up the libraries and stuff for how you want the Playground Express to interpret certain information. You set up the input as the microphone for audio input, and you're telling the code is trying to interpret the volume as a number, and that number correlates with color of light, right?
Correct. Yeah, that's what we're doing in a nutshell. I turned off this definition for the microphone and turned off the input because once you use the built-in function for the mic, it's going to read data differently.
Gotcha.
It's really hard to understand based on the H and CPP files exactly what the function does, but it takes in those numbers that we saw, that like 458 to 500 range numbers.
Yeah.
It takes that data and does a mathematical operation to it to turn it into a sound pressure level that has some kind of a response curve based on a range of frequencies and all sorts of stuff that's way down the rabbit hole into audio engineering. So again, I'm trying to strictly limit the information that I'm giving you, not because I don't want you guys to know stuff, but again, because I'm trying not to turn you guys into just sort of smoking holes in chairs. There's a lot that we're trying to do at the same time, but I'm trying to get you guys to be able to actually use the input, whereas if we were building circuits physically on the Arduino Uno, we would still be using analog for most of the things most of the semester. These, you have to use much more complex functions. There has to be a transform to run a digital to analog conversion and all kinds of stuff. So what I'm doing here is showing you an example of one of the things that you'll have to do in one of the assignments is, at least used to be one of the assignments, I think it still is this semester, using the sound pressure level in order to do operations. So that's
Gotcha.
that's kind of the next, some of the next stuff that we're doing. But then we also have to teach you about storing data into arrays, not just as a single integer. And then you have to look at, based on even what we're seeing here, even if I'm slowing it down, the rate it's reading data is so fast, the rate it's changing is so fast compared to what the output level is. We need to start learning how to do like moving average windows for data for sensor development. And that starts to get into actual like signal processing things that are usually reserved for like a signal processing class. So we're trying to teach you guys many levels and layers of things all at the same time. But because we have to use the stuff that's built into the Circuit Playground Express, we have to use these more complex functions. So I'm teaching you workarounds like this correction factor in order to make the things that are in the library, rather than completely redesigning the library from scratch and making it actually work correctly for the real hardware. I'm teaching you how to do some empirical correction as we go. And that's why calibration of sensors is so critically important, because you could plug a sensor in and say, oh my gosh, I'm talking at 120 dB. I need to go see a doctor because I'm as loud as a jet airplane taking off. No, the sensor is giving you wrong data. So yeah, we need to make some adjustments, but it should be interesting to you guys that we made a linear correction on a measurement and it gives a non-linear change in the output, because dB is a non-linear measurement. It's an exponential or logarithmic type measurement. So the sound at 120 dB is significantly greater pressure than the sound level at 80 dB. That's just how it works. So that's why these things are important, because if I could speak at 120 dB, I could thum people off of mountains at will, believe me. But that's clearly not a thing that's happened. The TV didn't go like crashing through the door as I spoke to the Arduino. So we need to understand realistic parameters and when our sensors are giving us complete nonsense. And that's why knowing something about the range of output I should see is important. So that's why it's very handy to have some of that background knowledge in hand. Okay, other questions? So I see some mid-level range. That's okay. 4s, 5s, 6s at this point is okay. Other questions?
For like the recording data and sensor input assignments, are we just doing those on our own, or are we going to end up like having like an example in class?
So that's why I'm trying to teach you these principles. So we've shown examples of how we can use the mic, how we can use the light sensor, and a couple of others in there. So the recording data. So they have some specifics already written out in the recording data. You want to measure 100 samples of the light sensor with 100 milliseconds in between each sample. So you guys already have some of that. And then you're using the serial plotter to be able to measure that. So we've shown you how to use the serial plotter today. So you have what you need to know for that. The responding to sensor input, has a document. So you'll want to review that. So we've already done kind of an initial calibration to this, but what it's trying to do is it's trying to do an output based on the temperature. So it's going to be using the output. That's where the buzzer function is going to be helpful. Let me pull that one back up. let me see if I know. There we go. So the buzzer, let me show you one of the things that it does. Okay. That brings up kind of an interesting thing, that this is one of the functions that we've used, but until you see it here, it's not going to completely make sense. I think this is the right one. Yeah. So when you do the circuit playground dot begin, what that does is that starts all of this stuff. That's what, when I say it starts the library that's doing all this gibberish in the background. So it's setting up these things that you can use. There is a buzzer that you can use for the output. So that is, I think they've got a demo in the examples of the buzzer, but I can't remember. I think they do. Let me pull that. Yeah, nothing's more fun than digging through hundreds and hundreds and hundreds of, here we go. Here is an example. So I'll jump back to the one we're working on. And you'll see it here. It's not as straightforward as you might expect, but let me share this. This thing is always in my way. Why would you cover the button with the other button? It's just dumb coding, that's all. So at the bottom here, I've added the circuit playground dot speaker dot say. So this is output to the speaker. There is, so that's why that CPlay buzzer is important. It also has the CPlay speaker shutdown. CPlay speaker shutdown is part of their sequence, and it gives you an example of how to use it. So let's see, I think you can do it by, I think you can do it by brute force, but one of the ways that you can do it is this way. So you can take from that H file the same line, CPlay speaker shutdown, to high. High meaning high meaning yes, turn off the CPlay speaker. So the value that this is looking for is a number value in I want to say it's looking for a frequency. So I'm going to take one. There's an example. Let's see. I need a couple of these. Does it have it? I don't know. I'm looking to see if this has it in the example. So I'm going to see if it will copy this over and compile first. Again, part of the problem with some of these. You only need a couple of them. I'm going to see if it will compile with a memory location for this from the example, because you have to create a this is a thing that needs a hex address in the memory in order to operate. I thought you could just add a frequency to say, so I can test it first and say, I can test it and see where it comes up with errors. So error in constant this might be looking for a string. Yeah. I think it's looking for yeah, it's looking for an address. It's looking for an address. So it has to be the say. I wonder if it's just speaker. Speaker 10,000. No, because so this is again teaching you guys more about compiler errors, which is start of next week's lessons because reasons. Yeah, you can't just use speaker, but I think you can use the buzzer. C play buzzer. I think you can actually just do C play underscore buzzer and then speaker shutdown. I think can't take in a zero as a function. C play buzzer high. I think this will compile. No, I need to do a digital write to that because reasons. Digital write to C play buzzer high. Delay 150 milliseconds. That'll be tolerable and survivable even by some roommates, unless they're a jerk, in which case do 500 milliseconds. All right. That should compile. Yeah, that will compile. I'm going to pull in a couple other memory locations because that's today. Let me set up those because they have to be set up as constants, and we get yeah, okay. There is a punchline to all of this. Okay. There is a punchline to all of this. That one just happens to be a much longer address. Um, no. Okay. No, that's right. Okay. All right. So those do have differing lengths for the address. All right. So that should be a constant. Okay. Yeah. All right. So I'm going to leave that. I'm going to test this first, make sure that it does compile, make sure that it doesn't do stupid stuff. Yes, it does compile, and I will drop it in. So this will output, I believe, sound to the buzzer for a second. Yeah, you can hear the diaphragm that goes back and forth. There's another function out there. I'll have to see if I can find it. But that won't fix what it is that I was trying to do there. So I'm going to pull over the other example to see if I can get it to actually see if I can actually get it to do this. the way that I think it works. Because that way you can at least see that I haven't completely lost marbles. No. I don't actually know if these memory locations are correctly assigned. I will find out in a second. It should have them. Yeah, that shouldn't be super duper helpful. So I will do this real quick. How did they spell it? Should have been spelled correctly, but I got to double check my spelling matches. That's why. Yeah, that's not how you spell whiskey, as it turns out. What do they know? All right. So whiskey is defined, tango is defined, foxtrot is defined. Why those particular characters? Well, based on how well today has gone, I will let you be the judge. I don't know that you can hear it, but it does actually work, which is quite impressive. Okay, so it can do it. There's a series of features that you can use, and that's one of the ways to do that. So some of that is in their example for male speech. They have a few different memory locations in that library. So make use of it carefully. All right. Any questions? Because I know we're out of time. A lot of people got to go to class. Yeah.
So I just wanted to clarify something with the assignments due this Sunday. So for part 4, the implementing the algorithm, it says like to use like 3 ingredients, and if it like if what we submitted for parts like 1, 2, and 3 are exactly within the parameters of part 4, can I just resubmit what I submitted, like the flow chart and the code the same way, or should I change it or something?
So once an assignment has been submitted, that's a totally different issue than some of the other things.
I mean, can I submit the same thing again if it fulfills all the requirements?
Yes, if it fulfills all the requirements, so long as you're meeting those criteria, that's totally acceptable to submit that. So yeah, that should be fine.
Okay. And then for the other ones, recording data and responding to sensor input. So what exactly are the goals for both of those assignments? I'm a bit confused. I think the responding to sensor input one, that one is just making a cricket sound, right?
Yes, correct.
Okay. And it's just a loop trying to make the Arduino, like submitting a loop function that
Correct.
just makes a cricket sound over and over again. That's it?
Correct. Yeah.
And then the recording data is that one, you're writing a code that records audio input and plays it back?
So it's No, it's not playing it back. It's just measuring the, so the recording data is measuring data from the light sensor, which we've already done.
Oh, that one. Yeah.
And it's looking for you to take 100 total samples with 100 millisecond spacing, and then plot that on the serial plotter in order to see what the sensor is bringing in.
Gotcha. So what we already
So it's
did.
it's very similar to what we already did. It's just using the serial plotter instead of the serial monitor. You use the serial monitor to make sure that what you're getting in makes sense, all of those things. But you're just using the ambient light sensor to do the next steps there.
Okay. Thank you.
Okay. All right. Any other final questions as we go to close out? If not, then I will see you guys next week.
Thank you.